Hello, PreCalc. Sorry I couldn't be in class today. Goals today, we're going to be talking about section 5.2. We're going to intro 5.2 today, which is the sum and difference formulas. This will take us a little bit of time today. I'm going to try to go through it as quick as I can. The goal today is to do a couple examples of your homework so it kind of alleviates your stress about what you need to do in your homework. Homework that I assigned yesterday, if you were gone yesterday, we did get new homework. It was assigned. It is due Wednesday, March 7th. You can see the homework problems on the board here. I'll put it up at the very end of the video as well so you can actually see that, and I'll leave that up there. The goal will be to do at least 2 homework problems, or at least they look like your homework problems. They're really, really close. And then we're going to intro the sum and difference formula. Now, the sum and difference formula that we're going to be doing on Monday are just about sine and cosine. We will eventually learn one about tangent, and I'll show you where those are at in your property sheet. So if you have your property sheet, that'd be a good thing to have out right now. But I want to just intro it and show you where it comes from, where they derive the formula from. It is intense on that part of the lecture today. You can just kind of watch that area. But when I get to the homework problems, I would expect you to be writing those down in your notes. But let's jump right in. Let's talk about our homework problems here. So the first example that I pulled out of your book was this one. It's very, very similar to the homework problems that you have. First step here, as they show you, you have the left and right side. You want to work with the more complicated side. So on this particular picture, this is the side I'm going to be working with. That's the more complicated side. I want to try to simplify it as far as I can to get it to look like this side. So there's little rules, like the basic rules that we talked about in class. You can do sine and cosine substitutions. So if you use your property sheet, which I'll show you here in a minute, you could substitute things out, replace them with sines and cosines, or versions of them. If they have negative signs, like this one, this is even an odd function. We'll have to take out this negative sign on the tangent, because tangent is considered an odd function. So we'll look at that on the property sheet. If they have fractions, we can potentially add fractions together, or find common denominators so you can add them, or multiply fractions straight across, or use conjugate rule. And then at some point, there's usually some type of Pythagorean identity on certain problems that have fractions. But that's the types of problems. I'm going to go through a couple of easy problems because that's what you have for most of your homework today. Stuff that we haven't discussed. We haven't discussed tangent a lot. So we're going to do one of those. And then the next problem that we'll do is kind of similar to this, but it's going to use a Pythagorean identity because we haven't done too many of those the last couple of days. So let's get started here. I'll show you the formulas off the property sheet here in a second that we're going to be using. Obviously, we're going to be using tangent and with a negative sign, so that's an even odd function. So let me show you the formulas here that are on your property sheet. So this is the property sheet that you have. The actual problem here that I want to discuss is the even and odd property for tangent. Now, sorry, this is very, very blurry, but the evens and odds formula for tangent is right here. Anytime they use a negative angle, you can take the negative sign and put it on the outside of tangent because it's considered odd. So that's what I want to make sure of. Okay, now let's get rid of that. But that's the property we're going to use on this problem. Now, the other thing we're also going to use is what tangent actually stands for. So we're going to do a little sine cosine substitution when tangent is also a fraction, sine over cosine. So those are the 2 properties we're actually going to use here. Okay, let's jump right back into that problem and actually try to simplify it so we can see, are the left and right side actually equal to each other. So the first step, let's kick the negative sign outside because this is an odd function, so that's negative tangent of x, and that's times cosine of x. Next, we're going to do a little substitution. So let me change my color here. We're going to take tangent and we're going to replace that with sine of x over cosine of x. And the negative sign is still up front, and we're still taking this times cosine. And then now what we need to do is we need to multiply these together. Now when you multiply straight across, these items are going to cancel. Now why that cancels is because this is over the number 1 that is a fraction. And so when you multiply, you can actually cancel things diagonally or vertically. And in this case, we do have cosines diagonally, so we can cancel those out. And when you multiply straight across, we get negative sine x over 1. And anything over 1 is just itself. So I can actually just write negative sine x. And that's exactly what we're trying to prove. So the right and left side are equal. Usually these problems take 2 or 3 lines of work. This one probably took 2, but I was kind of showing you where everything came from. But that's the type of homework problems that you're going to be doing. The first ones are very, very straightforward, very, very simple. In fact, we might have actually done them in class the last couple of days. But that's the first type of problem. Now let's jump into the second type of problem. This one also wants you to simplify and prove that the left and right side are equal. This one's a little more complicated. They have squares. By noticing the square terms, we're probably using Pythagorean identities, so we'll show you that on the property sheet. But I want to prove the left and right side are equal to each other. I'll try to start with one of the more complicated sides. I think that I'm going to probably start with this side, and then I'll try to prove it's the other side as well, that they're equal. Now, if I need to, like let's say I'm actually simplifying this thing down and I get kind of stuck, you can now jump to the other side and work with that side as well until you eventually can prove that they're either equal or not. But we'll look at the property sheet to show you kind of what property I'm looking at here. This part right here is not the exact Pythagorean identity. It looks close. The difference here, it has a negative sign. The Pythagorean identity has a plus sign, it has an addition sign in the middle of it. So it is slightly different, but that will help us for what we're going to do here. Okay, but let's go to the property sheet so we can actually see the property I'm going to use. So here's my property sheet. We're using the Pythagorean identities, which are right here. Sorry, it's a little blurry again. But the one we're going to be using in particular is this one. Sine squared plus cosine squared. We're going to use some manipulation of this. What I mean by manipulation, we can move any of these terms to the other side. So like I can move the sine squared to the other side and join the 1. It would be 1 minus sine squared. And we can use that for substitution. That's going to be the part that actually helps us simplify this problem down. So let me go back to the problem to explain. Okay. Now on this problem, the left side here, they have a sign over here. When you look at the right side, there is no sign whatsoever. So that's kind of a huge flag to me that I probably need to substitute the sine squared out. So if we went back to my property sheet, which I'm not going to do here, sine squared could also be written as, so I'm going to put in parentheses, this could also be written as, it can also be written as 1 minus cosine squared. Because you can manipulate that Pythagorean identity. This is the same thing as sine squared. Now there's still the negative sign out front, and there's still the cosine squared out here. But that's the trick, that I'm substituting out sine squared with a Pythagorean identity or manipulation of it, and this will help me out. Because now I can distribute the negative sign through the parenthesis. So this will turn out to be cosine squared minus 1 plus cosine squared. Because the negative sign will actually affect the negative sign on the cosine. So it makes it positive. And now I can combine like terms. Because the like terms that I have on this particular problem, I have cosines. And they're both positive. I can add them together. So there is 2 cosine squares. And there's a minus 1. And that's exactly what I'm trying to prove. So it's a little manipulation. The hardest part about doing this particular problem is understanding that I had to substitute out this piece right here with a Pythagorean identity. You just had to notice that it was not on the right side. So we had to somehow substitute it out. All right. Again, homework problems today. They'll be due Wednesday next week, Wednesday, March 7th. But this is the type of stuff that you're doing. It usually takes 1 to 3 lines roughly. There's a couple more challenging problems, which I told you about, 30 and 36. But again, I'm giving you multiple days to work on it because obviously this is your first attempt at doing trig identities. They're challenging, but it's also kind of a puzzle. You're trying to see how they work. The first homework assignment I'm giving you here is very straightforward. They give you what both sides are. So you're just trying to show that it can manipulate it into the other side. Then later on, we'll do problems where there's not a right side, and you have to simplify it on your own without any hints. But that's what your homework will be looking like. Now, let's jump into what I was talking about earlier today, that my goal today was to introduce the next section, 5.2. 5.2 is about sum and difference. Sum and difference formulas are when you want to add angles together or subtract angles to actually solve. What I mean by that is, and this is the part that I want to discuss today, was we've been doing problems where you could find like the sine of 60 degrees. We can do that, right? Because the sine of 60, you can just use your special triangles. That's a 30, 60, 90 triangle. The opposite of 60 is root 3, opposite of 30 is 1, opposite of 90 is 2, and the sine of 30, sine means opposite over hypotenuse for the 60 degrees. So 60 degrees, the opposite wall is the root 3, the hypotenuse, root 3, there we go, and the hypotenuse is 2, and there's your answer, right? It's root 3 over 2. that's fine, but that's only in certain angles, right? We can do it for angles of like 30 degrees, 60, and then 45s, because that's your other special triangles. But that's not what you're going to see in real life. Real life, gets messy. They're not perfect numbers every time. At some point we'll be having to do an angle like the sine of 70. And we have to figure out how to do that, to find the exact answer, potentially without a calculator. And that's what this stuff will help us with. It'll help us figure out ways that we can break 70 down into numbers that either add or subtract to make 70. And potentially these angles will be angles that are also special. Like they could be large angles, it could be obtuse that you're adding with another obtuse, or acute angles, but they have to somehow make 70, and then we can evaluate the pieces. So the goal today was to show you how they derived it. This is not easy. This is the part that you could probably just kind of watch. So I gave you two pictures here because these two pictures they're similar. What they're showing here is how they could subtract angles. So if we're looking at this top picture, we have an alpha angle, which is an obtuse angle. It's going into that second quadrant. We have a smaller angle, which is an acute angle in the first quadrant. And they want us to find the difference between them, the difference of the two angles, and evaluate it. So obviously they're putting this on a unit circle, as they're showing you here, that that this is a unit circle which has a unit length of 1 going to the as the actual radius of our circle. So by knowing that it's a unit circle, that's how they came up with these options. That the first dot in this coordinate here is the cosine, and then the second number is sine. Because on a unit circle, that's how it works. We had one of these on our actual test, right? That was, I think it was problem number 9. You had to look at a unit circle and read off that cosine was the first answer, sine was the second answer. That's what we're doing here. So this first one, by using the angle for alpha, this is cosine of alpha right here, and that's sine of alpha. This dot over here is cosine of beta, sine of beta, and that's how they get to those two locations, because they use the angle to get you there. Well, what we can do is we can use this concept to find the actual distance across. You can actually evaluate what certain lengths are, and that will help us find the sum of difference formula. I know it's really complicated, but this is how they derived it. So let me show you this really, really fast, and then we're going to look at the bottom picture, which I have here. So if I want to find the distance across from alpha to beta, right, from that one dot to the other dot, this is what you do. You have to subtract the x values, so cosine of alpha minus cosine of beta, and square that. And then we're going to add that to the difference in the y values, which are sine of alpha minus sine of beta. These are squared and under a radical. That's how you find distance across a length of segment. Now, to simplify this, if we actually square and you go first, outer, and last, we have cosine squared alpha minus 2 cosine alpha cosine betas. That's going first, outer, and last. I'm putting 2 parentheses down and foiling it, and then plus cosine squared beta. So that's just doing this first part here, squaring it, putting 2 parentheses down, actually foiling it out. Then the second part is the same with the sine. In fact, I'll just leave it pinkish purple here. That's sine squared alpha minus 2 sine alpha sine beta plus sine beta squared. And if we simplify things down, one of the things that I want you to notice that we have a cosine alpha, or cosine squared alpha, we have a sine squared alpha, and when you add those together according to the property sheets that we've been using, that's a Pythagorean identity, right? Cosine squared plus sine squared, well, that makes 1 when you add those two together. Cosine beta, sine beta, that also makes 1. And then the other two items, I don't know what those are, so negative 2 cosine alpha cosine betas minus 2 sine alpha problems writing that. It's not. It's because the picture's in the way. Huh? Minus 2 sine. It's just not letting me write that. Minus 2 sine alpha sine betas. There we go. So that's the distance across this length right here. Now that will help me because I can compare it to the other picture. Now the picture down below, I'm going to switch to a different color here. The picture down below is the same as the one up above. All they did was rotate this diagram down so that this wall where beta was is now flat against the x-axis. So they just rotate it. So the alpha angle is still the same angle. They just have it rotated down for the difference, I mean. So alpha itself is still same angle, beta was still the same angle, but they took the difference and they rotated down so the triangle's flat against the x-axis. And so why that's important is because it changes the actual values here. So as you can see, this first coordinate now is not, cosine beta and sine beta. It's now 1, 0 because they put it right along the x-axis. So it's a nice, easy number. And then the other ones are more complicated, like this one up here in the corner is the first coordinate for this dot right here, is cosine alpha minus beta because they've moved it, right? It's not just alpha anymore. It's now the difference because they've rotated the picture. And this one. Well, we can find the distance between these. So you subtract the x-coordinates, so cosine alpha minus beta, and we're going to subtract 1 and square that. And we're going to add the difference in the x-coordinates, or the y-coordinates, I should say, sine alpha minus beta minus 0 squared. If you square these, we'll eventually get cosine squared alpha minus beta minus 2 cosine alpha minus betas, and then plus 1. That's if you're going first out or last for this first item here. The second item, if we square, well, the 0 just goes away, and so we're just going to be squaring a sine, so we'll have sine squared alpha minus beta. And this is all still under the radical like before, this whole thing up here earlier. I go back to that pinkish color. This was still all under a radical. And the thing is, these were the same picture. I just rotated it. So these two distances we have here are actually equal to each other. They're actually the exact same angle. So I can actually just set these two things equal to each other. And why I'm doing this is because it will show me what the sum and difference formulas are. So in fact, let me go back to black here. And I'm going to set these two distances equal to each other. And I'm going to simplify a little bit. So I'm going to start with that pinkish purplish one. If I simplify that, that's 2 minus 2 cosine alpha cosine betas minus 2 sine alpha sine beta. That's all under the radical. That's equal to this thing down here, which if I simplify this part in green, I have cosine squared and sine squared. That makes 1. That's doing these items, right? Adding those. That makes 1 because it's a Pythagorean identity. I'll add that to another 1, which is right here. So that actually makes this a 2 minus 2 cosine alpha minus beta. Now, when we actually square both sides, because I have radicals, right? When you square both sides, you actually take these parentheses and you square them, because that's a property that is a property you can do on any type of problem because it's a property of equality. The radicals would go away. So if I got rid of the radical, let's see if I can actually erase these. I don't know if I have the skill for this. So if I square these, the radicals would go away. And now I can move things right and left side, and a lot of this stuff will start canceling. So if I drag this 2 to the other side, yeah, it's gone, right? The 2's are gone. If you notice, I do have certain things that are in common here. as you can tell, like there is a -2 right here. There's a -2 on this thing. I can factor that out. So if I show you how to factor that, if I factor out a -2 out front, that is cosine alpha, cosine beta. Ooh, I don't need that parenthesis there. There we go. Plus, because I took off the -2 and I put that out front, sine alpha, sine beta. And that's where the parenthesis ends. And then that's equal to the other side, which is -2 cosine alpha minus beta. And then I can divide both sides by -2. Well, if I divide both sides by -2, the -2's are gone. And that is your difference formula for cosine. Now, what that is that's how we can find the values of cosine when you want to subtract angles on the inside. So let me highlight that here. That if you had two angles that you wanted to subtract, maybe make 70 degrees, you could go 90 minus 20, right? That's 70. You could subtract the two numbers in here, and all you have to do is, now that you know your alpha and beta 90 minus 20, you could plug those values in to these spots respectively. And you could evaluate them each individually by themselves. So, if it was 90 minus 20, you could plug 90s in here and here, because those are my alphas, and then the 20s go in here. And this could potentially give your answer for the cosine of 70. That's why this formula is important. This is the stuff we're going to be talking about Monday. I won't do the whole deriving thing. We're just going to talk about how to use it very, very quickly. Okay, hopefully that made a little bit of sense. I know that was really difficult stuff, just throwing that at you all of a sudden. We'll discuss this more on Monday, but it is insanely important that we get the fundamentals of where this thing was derived from. All right, so talking about the homework itself. Sorry, I went off on that little tangent there, but homework due Monday. Or sorry, geez, I keep saying Monday. It's due Wednesday, March 7th, page 594. Make sure you're doing 2 through 6 evens, 9, 11, 14 through 20 evens, 23, 25, 30, and 36. Remember, the last few get a little lengthy. The first one's very straightforward. 2 to 3 lines, done. The last ones you have to try to simplify as best you can. I'll be back Monday. We'll discuss. Good luck.